Good afternoon, everybody, and welcome you all to this Institute Colloquium. And we are very happy to have Kanishka with us, Professor Kanishka Biswas from JNCASR. And I request our director, Professor Tanushri Shada Sutto, to kindly introduce the speaker.
Uh, so I think it's a good afternoon, everyone. I think it's a pleasure to introduce Kanishka Vishar to this audience. Many of you, I think, are well known. At least Kanishka is known to you. So Kanishka did his masters and PhD from ISC Bangalore, and his PhD was with none other than Professor Sena Rao. And after that, Kanishka did his postdoc in Northwestern. And since then, he is back in JNCASR, and he is probably one of the most promising solid state chemists I know of. And his area of research is vast. He has worked on many different things, but one which probably is the highlight are the thermoelectric materials, and that has a connection to the modern terminology which are called quantum materials, because there is a kind of a uncanny relationship between thermoelectric materials and topological materials, the reason for which is not completely known, but understanding that, we expect will basically uncover many of the things. So only common thing probably is some of the spin orbit coupling which is needed and etc. But that's still not a profound understanding. And Kanishka has been working quite seamlessly. And I mean that's another thing. One can work on many different things, but it is very important for a young researcher to find out a niche area, and that's what Kanishka has been able to do, and which is reflected also in various awards that is listed already in the poster. But worth mentioning Shona Janti and Shanti Sharu Bhatnagar award, and also at a very young age she is the fellow of Indian Academy of Science. So this just award brings something, some recognition to your good work. So I think he sets a perfect example how to create your niche area and how to continue doing excellent work on that. So I do hope we'll get some, glimpse of all the work he is doing in 1 hour. It is not possible to cover everything, I know, but I think he will talk about two of his latest publications.
So, thank you, Tanushriti, very much for this nice introduction. And we have raised the important question: how thermoelectric and topological quantum material is connected. And let's see, at the end of this talk, I have some answer to give you and all of you, which is the connection between these two things. That's the area we are actually looking for, how to answer this question. So the materials characteristics are very similar for these two things. So, and thanks all of you for this invitation. And I had a excellent day discussing with many of you, science and many other things. So hopefully I'll try to explain something and in this area. So today I'm going to talk about this newly discovered chemical bonding, which is metavalent chemical bonding. So which is completely or not fully completely, but it's different from covalent and metallic bonding, and of course from the ionic bonding. And that's probably the connection between these two things. So thermoelectricity and quantum material, because the quantum government has declared quantum mission, and quantum materials is one of the pillar. And I believe as a chemist, I have, or we as a chemist, we have the responsibility to understand the chemical bonding in the quantum material, which is extremely important. And we found out from some of last two years research, this is one of the unique bonding which is actually present in quantum material, and it connects quantum material and thermoelectrics. With that, I'll give a very brief introduction of thermoelectrics. So thermoelectric is a direct effect. It can convert temperature difference to voltage, which is known in two important effects for students. So first one is Seebeck effect, which is discovered 200 years back, while you have a temperature difference, hot end and cold end, and this p and n type semiconductor connected in a series, in electrically series but thermally parallel, it can generate voltage. And at the same time, if we provide voltage, the same device geometry, you can get temperature difference, and voltage can be used for refrigeration, and this is called Peltier effect. And there are many products based on this Peltier effect. I'm sure these assemblers are having many instruments which is having this Peltier installed. So today, today's energy demand, actually this effect come very important. Why it is important? Because this, you see, this is the total energy conversion in 2019 and to the world in 2019. This is the energy conversion phase is noted. So we consume energy in terms of coal, petroleum, and natural gas. So we burn coal in NTPC and get electricity. And burning of petroleum and natural gas gives rise to like rather transportation and industrial sector. Right? So after use of enormous amount of energy in terms of combustion of coal or combustion of petroleum and natural gas, we only use 35%. Actually, 65%, 65 to 70% goes as heat as a waste heat in the nature. So how to convert that waste heat to some important form. So that's why if we now see this hot end of this Seebeck effect can be used as a waste heat end in the combustion processes, and we have this efficient semiconductor, and this cold end can be room temperature or near to the room temperature. Then this waste heat can be converted to this cold end. So that is called thermoelectric energy conversion. So that's why many of us are working in this field, and that's why this is a very important field because it has the stake in energy conversion in next couple of years. I'm not saying that thermoelectric will solve all the problems, but it can go hand in hand with many. I'll give you some of the examples here.
So yeah, so maybe so what would be the efficiency of a thermoelectric?
Yeah, so
compared to a solar cell?
the solar cell efficiency is much higher right now. So
Much higher.
solar cell efficiency is perovskite solar 30%. Okay. But thermoelectric efficiency are in my lab it is around 14 to 15%. But that is quite good. I'll tell you the field where solar and thermoelectric can go hand in hand. Next slide. So, for example, like what are the uses? In large scale, it can be used in power plants like chemical, thermal, nuclear, steel. And then I work with a steel company personally. So time permits, I'll give you one slide example how we work with Tata Steel in this direction. And then medium scale, it can be used for automobiles. Automobiles exhaust pipe will radiate lots of heat, and the companies like BMW, GM, Ford, they have this thermoelectric generator installed in their car, so they make the car well efficient. So now space power generation. This actually space power generation by NASA and the Russian Space Foundation are using this thermoelectric technology for last 40 years, but for their different mission. For example, like if we send a spacecraft to say Mars mission, right? And then Mars mission we cannot use solar cell because Mars is far from sun. Solar cell intensity which is 30%, that is become 1%. How do you power the electronics of a spacecraft, right?
Heat generated.
Right.
It will also be coming from sun only.
Exactly, but that will tell you how they have done it. What they have done it, so they have taken in a sealed glass jar, inside a glass jar, plutonium oxide. Plutonium oxide, plutonium half-life is 28, and it decays and gives the heat of 300 to 350 degrees centigrade, and that glass jar was covered by a thermoelectric generator. And that runs for 28, minimum 28 years in the space craft near the Mars mission. For many Mars mission, at least 35 mission, NASA has used this radioisotope thermoelectric generator for their deep space mission. So that's why. So this mission actually put thermoelectric in the table, so it can convert heat to electricity in medium scale. And it can convert in larger scale also. So then the new uses are solar thermoelectric. So these are upcoming field. So as he said, like solar cell efficiency is touching say very high. So we know solar cell are going to convert light to electricity, right? So that is basically my UV or like visible part. What about the IR part of the solar? That's the most important part of the solar light. IR part is the heat. So if I install thermoelectric generator just below the solar cell, the efficiency will be much more. So thermoelectric has to go hand in hand with other technology. So now we have mobile phone, laptop, and our government is thinking towards electrical mobility, right? And battery heats. Thermal management of the battery is very important for me. So this thermoelectric field can go with the battery, so that battery heat can be also converted to the electricity, and that same electricity can charge the battery. So this is a new field, battery with thermoelectric. So this is the way it's going, and also the other uses could be the data center. So we have a huge data center throughout the world, and that generates huge amount of heat. So that's like several uses of thermoelectric, but I'll not bore you with the application. Today I'm going to talk about fundamental science mostly. So the fundamental parameter which governs the thermoelectric figure of merit is basically this is the ZT, which is thermoelectric figure of dimensionless thermoelectric figure of merit. We purposefully make it dimensionless so that we can compare one material to another. And the numerator is Seebeck coefficient, which is nothing but how much voltage one material can generate unit temperature. So that is basically delta V by delta T. And all of we know what is electrical conductivity, how fast charge carrier can move from one end to another end of a material. So now the numerator is having only electrical transport, whereas denominator is basically the thermal transport. And the thermal transport, thermal conductivity has two parts. The first part is the electrical part of the thermal conductivity, where charge carrier carries the heat, which is directly related to the electrical conductivity by Weidemann transfer. So that means we don't have much control on the electrical part because we need high electrical conductivity but low thermal conductivity. So this part we generally don't touch because that is not in our hand. Whereas the lattice thermal conductivity, which is carried by the phonon, that is the intrinsic parameter of a material, and that is only independent parameter in this equation because Seebeck and sigma are related by carrier concentration as well as which is related to Mott equation. So, can you decrease the group velocity of phonon or block the phonon in a solid material to have high density material? That is the challenge. So, as a solid state chemist, I think the problem is slightly different way. We need a property of metal which will have high electrical conductivity, property of semiconductor which will have high Seebeck coefficient, and property of glass which will have high low thermal conductivity. So, can anyone synthesize a material which will have property of metal, glass, and semiconductor in a single material? So that is the grand challenge in this field. So we'll show some of the examples, and we may see some of the properties like metal and glass together in a solid. So more scientific way to tell the decoupling of the electronic transport from the thermal transport in a material. So you have to channelize electron and phonon into different paths so that you can get high Z. So that's the key to have good thermoelectric material. So all of us knows what is lattice thermal conductivity. This is governed by the quantized lattice vibration, which is nothing but the phonon. And for a simple one-dimensional lattice, I have only one acoustic phonon when atom vibrates in the same direction, which is nothing but the sound wave in a solid material. Whereas optical phonon or atom vibrates in different direction, and that generates basically the dipole moment, so that you can track by spectroscopic technique such as Raman, Terras, or IR technique. But generally, the material will most of the time will have optical and acoustic phonons are always very gap. So how to actually scatter this acoustic phonon? Because acoustic phonons are generally responsible to have thermal transport in a solid. So the game is basically how to block this acoustic phonon. So over the years, people have studied many ways to block this phonon. So in a heavy metal based solids like heavy metal based selenides and tellurides, the phonon wavelength are having in the range of 1 to 20 nanometer, which actually carries the heat. Okay. So we have to block those particular phonon which carries the heat. So that means you have to have similar size object in the solid. So, for example, like 1950s and 60s, scientists from Russia and US, these two are the country actually doing thermoelectric research from those time because of the space mission. So they have done it. So they made like grain boundaries by like mechanical annealing or material science synthesis technique. So those grain boundaries are actually micron size. So those are not scattering the right phonon. So there is a decrease in thermal conductivity, but not too much to have a get a very high depth. So then people have done solid solution. Like say the champion materials lead telluride, people have done lead tin telluride or lead telluride selenide, this kind of solid solution. But atomic point defects are also in the range of angstrom. So that they are also people are not scattering the right phonon to scatter the to decrease the thermal conductivity. So for example, this is the lattice thermal conductivity versus temperature plot for the champion material lead telluride. You can see this is 2.2 watt per meter Kelvin, and it decreases up to say 1.2 watt per meter Kelvin at high temperature. So, as I told you, in 1950s, 60s, people have done solid solution point defect that decreases the thermal conductivity, but it does not go to the glass. We can calculate the theoretical minimum of a thermal conductivity for any material if you know the sound velocity. So, from the kinetic field, you can calculate the glass limit. But this paper first time has been done in 2004. They put nanoprecipitate in the lead telluride material. So these nanoprecipitates are the size of phonon beam which actually carries the heat in this kind of solid. So that decreases the thermal conductivity so much that density shoots up first time above 1.5. Later I came into this field And then we have created like hierarchical nanostructure, nanomeso architecture, like the grain boundaries, nano precipitates and point limits, so that all length scale phenomena has been scattered and electric went above. So now,
But does it not compromise
Electron.
on electrical?
next slide. Okay, so again you asked the right question. So so extrinsic nanostructure decreases the thermal conductivity, but it decreases the carrier mobility, right? So we are compromising with the carrier
So
transport.
is it like if you have topological material, topological around the grain boundary?
Right. So, so this is this grand challenge has been remained for this field for 15 years. People, these nanostructures are not new. The nanostructure started from 2004 in thermoelectrics, but this problem has not been solved. So we asked the question, like when I joined JNC like 11 years back, we asked the question: can we have very high electrical conductivity with very low thermal conductivity, like glass and metal? Can we have these two in a single material, right? So how to do that? So in order to do that, recently we have shown there is a way creating nanoscale cation ordering, but not by foreign dopant. So cation itself will order and form nanoscale cation ordering, and that delocalizes the electronic states. And then we have high mobility and low thermal conductivity that we have published in 2021. But I'm not
Just one question.
Sure.
Just some more details.
Yeah.
So I understand you probably have within the nanoscale certain thing,
Yeah.
but this nanoscale, if I understand, these nano objects are embedded in some
Matrix.
matrix.
Yeah, yeah.
So wherever you have the interface
Yeah.
between this nano object and the matrix,
Right.
there will be also electron scattering,
That's what,
which
yeah.
I cannot have.
Yeah. So that's the thing. Yeah.
So you
that-
will have that.
Of course, we'll have. But if I have a endotaxial nanostructures, so there we can avoid. So that's what we have done it in this paper.
So what do you mean by endotaxial?
Endotaxial means the lattice will be completely matched, but it will have some strain. So that will scatter the phonon, but not the electron. And other way you can do it by see electron mean free path, you can hole mean free path. You can tune such a way it will be an angstrom, so it will pass through. But phonon mean free path is a nanometer, so we can create two lengths. So we have created all these things in our material. But today I'm not going to talk about
No,
it.
no, no, I just,
Yeah, sure. So this paper is mostly based on that. So then to search for the material as we should have high electrical conductivity and low thermal transport, we came to this topological quantum material. So as most of you know, this topological quantum material, one class is topological insulator, which is nothing but having strong spin orbit coupling, band inversion, because this I am talking about strong topological insulator, odd number of band inversion, and it has a metallic surface state. And it has a scattering less transport because the spins are long. So we can have very high mobility in this material. At the same time, these materials are heavy metal based chalcogenides, which are having heavy already starting with heavy metal, so that the thermal conductivity is kind of low in this material. So we can work with in this material to have high electrical transport and good, bad thermal transport. Yes.
Also, these materials, S is large.
S is large. Yes,
Yes.
because of
So
the
actually, you can also think in a way that S large and sigma large.
right. Right.
Keeping the K, keeping means so three ways of looking.
Exactly. So that's what I'm going to tell also. S is large because of the band inversion and all.
Yes.
But here you were talking about the conductivity of the surface state.
Exactly.
only.
You have to use
So your device has to be such that I just use the surface.
right. Exactly.
I have a question. So suppose you made your these small grains to be this topological material, right? So the grain boundaries will have this topological states only.
We don't know. We don't have a proof for that.
No, it will have.
It will
So
have
what
that.
he is saying,
Yeah.
you
Basically,
have a
yeah.
topological insulator.
Yeah.
Yeah.
And let's say your matrix is a normal insulator,
Exactly.
Okay.
then of course the boundary will host some surface
Yeah.
state,
But
which will be
but
protected.
how the interface will be, we don't know.
No,
So
the
it doesn't
surface,
matter.
that
Shape doesn't
interface.
matter.
No,
Shape doesn't
no,
matter.
it's not the shape. But I'm also expecting it to be,
Yeah.
but how like see if I have a normal insulator
Huh.
and I have a topological insulator nanostructure.
Right.
Okay.
Right.
So this is no more a simple surface of a topological insulator, right? So it is interface
No,
with
but
the
it will be a,
yeah.
wherever you will have the interface,
Okay.
by construction it will
Yeah,
be a
we gain some amount of conductivity, but that will be masked by the bulk conductivity of the matrix.
That's
Because-
also
yeah, because
No,
That's also-
so I'm expecting there will be a percolation transition. At point you will get the full conductivity to
exactly, but you need so much nanostructure to do that.
Yeah, to reach the percolation.
Yeah,
Yeah.
that is true.
So that is possible. That is
But that will also reduce thermal
I think
conductivity. Sorry,
this
yeah,
will
yeah,
lead to a
continue.
complete
Yeah.
discussion.
Right.
Divert you from
No
this.
problem. Yeah, sure. So then another topological quantum material is topological crystalline insulator. We have strong spin orbit coupling, band inversion is given, and metallic substrates are protected by the crystals in it. So that material also can be used, which is nothing but like solid solution of lead tin telluride. So that is one of the best thermoelectric PBT, not tin telluride steel. So and bismuth telluride is a very good thermoelectric, not bismuth selenide. So then we want to much deeper and try to understand like bismuth selenide structure, and it is a strong topological insulator. But when you have a layer of topological insulator, then it becomes a weak topological insulator because the metallic substrate will get only some of the detection. But those materials are generally van der Waals heterostructure. And once we have a heterostructure nature, thermal conductivity will die down much faster. So this material would be a very good thermoelectric, which is weak topological insulator. Time bargain can be one example. So now, how these two things are connected? Okay, so material characteristics: heavy metal based chalcogenate, the narrow band gap semiconductor. These are the two important points which is required for both the field. Which heavy metal based chalcogenate heavy gives rise to low thermal conductivity. Narrow gap band gap semiconductor gives high carrier mobility and good Seebeck coefficient. So it comes to thermoelectric, and this narrow band gap with heavy metal gives SOC, and band inversion it becomes topological. So this
Are we talking about only nanostructure or within the bulk?
bulk.
Bulk, right? Because nanostructure there will be different.
I'm not talking nanostructure, the problem I said, and then I can do the topological. So we're talking about only bulk material. So these are the material characteristics and how these two fields are connected. Now, as Sonoshid asked the question, like, okay, these are the only material selection. How these two things are connected, right? So what we believe, reading the literature, also talking to people, and doing research in this area for last 2 years, and trying to understand the question: can chemical bonding is the connection between these two? And that not many people are talking right now about the chemical bonding with the topological quantum. So now the new term came, new type of bonding came in last 2-3 years is metavalent bonding. Okay, so metavalent bonding, the name is came from meta from metal and valent from covalent. Okay, so it's in between metal and covalent. I should not say in between; it's different from metal and covalent. Let's try to understand what is this bonding. So now I have metallic bonding means electrons are fully delocalized. Okay. And in a covalent compound, electrons are localized between two atoms. So two electrons are shared between two atoms form a covalent. But that we know from the school, like chemistry, right? So in one case I have localization of electron. Another case I have fully delocalization of electron. So what this group, Mathias-Wittig group, what they propose? So metavalent bonding is actually they say that it's the tuning between electron localization and delocalization. So let's see what try to understand what is there. So if so they have plotted electron shared versus electron transfer. So if I have electron shared, so basically two electron is shared, nearly two electrons shared, the best covalent compound, you know, that is the diamond, right? So it comes here. So this is the ideal covalent bond, but carbon, diamonds, silicon, germanium, and some of the tetrahedral compounds, all most of the highest covalent compounds are tetrahedral. Okay. So it comes here, and now if I come in this region, electron transfer, that means it's ionic. Okay. For example, the one electron transferred in sodium chloride. That is like one example of ionic. Now it depends on the charge. Where I have 1.5, so then so BAT and all this BAC, all these compounds in this coming. So
I'm surprised BAT is close to an ionic bonding limit, because after all, I mean, in the sense that BA is quite extended, right? You wouldn't expect. I mean, CAT you would expect.
no,
Or
BAT also ionic bonding. It's not say alkaline art. So generally they form basically ionic bonding. So you
I mean,
see
it would be more covalent, right? Than you go up the periodic table.
it's not electron shared. Actually. BA is down.
No,
BA
but
is
it
more
is
electron.
true that in terms of electron shared,
Yeah.
you actually
Then
have BATI above CAT.
Yeah, that is a small difference. That is
You
very
will
small
have-
difference. So, but
Yeah.
it's not here near two. Generally, two electrons are shared.
Calcium.
Yeah. So calcium, strontium, barium. So barium is there.
But they're almost similar location.
Yeah.
So I'm little like, I mean, you would think that they would be.
But covalent bonding is here. Say red colors are covalent bonding. where the around 1.5 or above, basically electrons are
I mean,
shared.
it's
Yeah.
good.
Yeah. And then we know about resonant bonding, right? It's a graphite or benzene, where actually 2.5 electrons are shared. So 2 electrons shared by sigma bonding, and 0.5 electron is shared by pi bonding. So this is called resonant bonding. So now the metallic bonding is basically 0.5 electrons are shared, where we have like aluminum, silver, copper, gold, all these things will come in this way. So now they pointed out there is a green region where 1 electron is shared between two atoms.
And
So this,
how is this determined? How is this determined?
I'll tell you all the descriptor. I'll tell you.
Okay.
Give me some time. I'll tell you all the descriptor in another 1 or 2 slides. Okay. So these kind of compounds. So this compound we worked in AGSB T2 in last 2021 paper, and then GET, PBT, SNT. These are the few compounds they told about this. And these compounds are having 1 electron share. Now the question is how 1 electron is shared. So germanium, tin, lead, the electron configuration is carbon group, right? NH2 NP2, 4 electrons. But these compounds are octahedron. So you need 6 electrons to form a 6 bond, but we have only 4 electrons. So this is basically an electron deficient extended compound. So bonds are highly polarizable, chemically polarizable. So that means you can actually bonds are very soft. So what we believe, because of this bond softness coming from the electron deficient bonding, this compound shows very low thermal bonding. This is one of the reasons. Okay. So now, so this group they have worked in this metavalent bonding that they are most of the interest are on the phase change material. But what we are believing this is very important for quantum material and thermal, because these compounds are very important for both the fields. So now, like you can ask me question, okay, what about B2AC? Right? This is a classic compound in chemistry where this three-centered two-electron bond has been discovered for many years ago, and Roald Hoffman has worked in this compound as well as this compound, like the HCF, which is the hypervalent compound, while the electron bond order for metavalent is 0.5. Okay, it is two-centered one electron bond, and resonant bonding is 1.5 as I told, and this hypervalent is 1.3. So these are distinctly different from it, as well as from resonant and hypervalent. Metavalent is different. But the question right now, chemists are asking, molecule for a simple molecule, it is known for the long time, but what is not known, how the bonding behaves in extended solid. So basically, if you see the question is two linear two-centered one electron bond is equivalent to three-centered two electron bond, which is already known in molecule for many years. Is it same or different? Extended system, but that question is not answered. Another question is metavalent bonding another name of a charge shift bond? So it is hypervalent bonding. Actually, that question I also, but I don't have answer right now. So it is same or different. So people are asking a similar type of question in this field. But what we believe is this metavalent bonding, it creates a completely different region from covalent, metallic, and ionic, and also resonant. And they are one electron is shared between two bonds, and this is the electron deficient bonding. That must be understand. So how to now probe metavalent bonding? What are the like descriptor? Which is metavalent bonding, which is not the metavalent bonding?
Can I understand metavalent bonding as a combination, partly ionic and partly covalent?
Actually, no, because there is no ionicity, because the atoms are not holding the electron. So they are leaving the electron to share, but the number of electrons shared is less compared to covalent.
So, if I understand correctly, so it is not at bond center, but it's shifted a bit. The electron cloud is the maximum of the electron cloud is on at the bond, but not at the middle of the bond.
So not always, so because if I have if I show you some of the ELA for charge density plot, you will see that density is more like a covalent bond.
Yes, but where the maximum is sitting.
Yeah, maxima in the bond also.
In the bond, but not in the middle of the bond.
Not in the middle of the bond. That we can I cannot generalize at this point because I don't have much compound in the hand, right?
It should not be in the middle.
That will see.
If it's not in the middle, then it's like ionic, right? It's more with one.
But we'll show you some of the cases in the middle also. Like,
I see.
yeah, but these electrons are
So
shared.
resonant bonding.
Yeah. So resonant bonding, the electrons, sigma electrons are shared. It creates carbon-carbon covalent bond, and pi electrons actually cloud. We have the resonance.
Benzene.
Yeah, benzene. So that's why it's 2.5, more than 2. Because the sigma plus pi. But here in diamond it's only sigma bonding. Okay. But here only sigma bonding again, and also pi bonding. But the electrons are only shared. It's much lesser. So you can tell this is the electron deficient bonding, and we cannot quantify this is the covalent or metallic based on the property. So let's see what are the property of this bonding. Okay, so
sorry, now I'm getting even more.
yeah,
So
even I am also confused.
I
Okay,
because you
yeah,
see, like you are saying that it's a more or less than in single particle picture, this looks okay.
yeah,
But if you have a multi-valent, what is determined by the any of the even covalent, there's no perfect covalent bond.
exactly. There is no
Always
perfect.
partial charge.
No.
Right? So when you are saying the metavalent, how that is different from that partially charged covalent?
Exactly. So if you see the perfect covalent is 2 electron is completely shared, right? But you see all the dots here near 1.5. So these are never I said that these are perfect covalent. But this is even lower than near perfect covalent. Okay, and it is in between the near perfect covalent and metallic.
So is it just a quantitative number that making it different, or is there some? So you gave a localization, delocalization kind of picture.
Right.
So that I understand from kind of background of
So
Anderson
I-
localization.
yeah.
What you mean?
No, that is not Anderson.
No, I'm saying that. So there is a critical phase between localization and delocalization. That is
Exactly.
called Anderson critical. I know how the electron behaves there.
Yeah.
So I know physically how that will be different from localization.
Exactly. So
Here I am not having that critical phase.
I'll tell you how. So this is let's say I have 4 electrons for a left dendrite, one P dendrite, right? Four outer shell electrons. So this 4 electrons can form four covalent bonds, right?
Okay.
The compound should have tetrahedron, right? But the compound is octahedral. So 4 electron is shared between 6 bonds here. Okay. So this the sigma electrons or into tellurium or into not selenium, so sorry, into tellurium, that bond not having uh, 2 electron, which is only shared between tin and tellurium. It is having per bond is having 1.5 electron, which is the 4 electrons are shared between 6 bonds. So what I mean, can I draw somewhere? So I think I understood your question. So in metallic case, I have a complete delocalization.
Yeah.
Covalent case, the 2 electrons are localized between one bond, right? Here, 4 electrons are partially delocalized between 6 bonds. So this is, but not in the full compound like a metal. Okay. So it's in between completely localization and completely delocalization. In a local level, it is basically you have a delocalization of bond of
But
electron.
that's because you have a deficit of
Exactly.
electrons
Yeah.
to satisfy those bonds completely.
Exactly. So these bonds are actually not octet.
It's not
So
optimal.
basically, we are not satisfying.
You are
We are
not
just
satisfying.
making them little bit happy. But that actually tunes many property of that medium. So this is an electron deficient bonding which are highly chemically polarized. That even those bonds are very soft. So that's why the phonon
The thermal conductivity.
thermal conductivity.
Group velocity will be.
Yeah. So this is a different idea.
But I think if you apply some external perturbation, then this concept might change. For example, pressure.
Yeah, of course.
High pressure, then this will be a continuous change from one point to other point.
Exactly.
Yeah. Here you are categorizing discretely to one.
I'll show you some pressure data also.
So then this idea
So
completely
basically, the compound which are highly covalent, the
Yes.
pressure transition is much higher pressure, higher
Yes.
GPa, say 60 GPa. But this some of the compounds shows pressure transition in 2-3 GPa.
Yes.
Okay.
Very
So
sensitive to ambient.
yeah, so I'll show you the pressure.
Kanishka, I mean,
Yeah.
it's still you.
No, not in, like I know that this topic is very
Yeah,
new,
that's
so
true. I mean, I would say that this is still a covalent bond. Only the number of the electron is less because what you are doing is it is equally bonded to different structure.
Right.
It will keep getting delocalized.
Yeah.
Covalent also, you are saying that it's only confined to neutral orbitals. It's not true actually. Even if you take the electron deficient system and have the bonding proper form, it will keep delocalized and extended.
exactly how much? Molecular system, you're talking, how much? So can you tell me this kind of bonding has been?
I think we will reserve
Yeah.
this discussion
Okay. Okay.
for after your talk
Sure.
because there will be so many because
Yeah.
it's a new concept.
Okay. So then sort of the descriptor. So come back to Priya. So the descriptors are basically this has a moderate electrical conductivity. Metals are having very high electrical conductivity. Generally, this compound shows moderate electrical conductivity in the range of 10 to the power 2 to 10 to the power 4 Siemens per centimeter. And then high optical dielectric constant. These compounds are showing. And then it is having high effective coordination number, which is no covalent, and these are cross metallic. So electron transfer is low. which is not ionic, and high bond effective charge or high enharmonicity. This is important because this is important for thermoelectrics. So the distinct bond rupture mechanism that I am not going to tell much. So if you see, this is the electrical conductivity for ionic compound very low, covalent is low to moderate. Generally, all the system falls in this range. And these compounds like falls in this range 10 to the 2 to 10 to the 4. Metal is above 10 to the 5 Siemens percent. So then effective coordination. So 4 and 6, these are the classic ionic compound, and here 8 like octet is rule is always applied covalent. And then this 8N rule is not followed. As I said, like 4 electron cannot form 6 bonds, right? So and then metallic is BCC or H, coordination number is 8 or 2. So and then optical dielectric constant, either you measure or calculate, it's this very high value above 50. And bond effective charge is also high, 4 to 6. Bond effective charge, I think some of you know, which is nothing but it's not a formal charge, but how atom what is the charge on atom if that tends to be displaced. So then mode specific Gunnessian parameter is also high, which is nothing but like how much we can put strain and how strain we can put under the phone. So this value tells that the quantification of the enharmonism. So this is generally close to 3 or above 3 for this metavalent compound. So we'll check all these descriptor and tell this compound is metavalent. So to start with this, like germanium selenide, which is actually a very well-known compound for a long time. It has exactly same structure as SNSC. SNSC is a famous compound in thermoelectrics. So it has having a covalent bond, GESC covalent bond, like a phosphorine type structure. Okay, and it has a van der Waals bonding between two layers of GESC. And this is a covalent compound, and it has a van der Waals gap. Okay. And this was predicted to be very high thermoelectric by theoretical paper. Okay, ZT of 2.5, but when we measured it, it's actually 0.1. So first time we measured this component, it was 0.1, and we surprised. Like, but GAC cannot be like very good thermoelectric alone. That's what we understand. So then what we have done, because of its covalent bond, it cannot be a good thermoelectric. So what we have done, pristine GAC have the carrier concentration of 10 to the 4 to 10 to the 16 per centimeter cube, and its electrical conductivity is 0.004 Siemens per centimeter. It's a very bad compound for thermoelectric. So then what we have done, GESC we alloy with AGBI-T. Okay, so AGBI-T is a important compound in thermoelectrics. So slowly alloyed with, so if x equal to 0, this is orthorhombic structure. You see the dot of it. So this is like lower symmetry structure orthorhombic. As soon as I alloyed with 10% of AGBI-T2, it becomes R3M. So R3M pure compound, and it has this structure. So R3M structure has 6 bonds. Germanium has 4 electrons. So we believe this is a metavalent bonded compound, and we will give you the descriptor. And if we allow more, 30%, it becomes FM3 by. So basically, it becomes rock salt. Again, much more compact octahedral. So this work has been done by my PhD student Devotam, who is also living, almost living now. So let's see like how the bonding nature of this compound changes and how it uses the its property. So in order to do that, we first measure electrical conductivity. So this is GESC, very low. As soon as I go or alloy it with 8 to 10%, you see the electrical conductivity comes in the range of metavalent like 100 to like 300 Siemens percent. And so then we have the carrier concentration also improves. So it has moderate electrical conductivity, high effective coordination number. So dielectric constant calculated by units, this is around 30, is very high. So then high bond effective charge. So Ge is supposed to be +2, but these are the charges for each atom. So this follows all the descriptor of metavalent bonding, and that's why we and then the has calculated the electronic structure. It has multi-value, as we said. Like,
tendency for this material to be
wait, okay, because R3M, right? So very good question. So I'll tell you. So basically, we see multi-value, and multi-value is very good to have high Seagate value. So this compound shows very high Seagate value. So then we have calculated the phonon. Yeah.
Your system is disordered, right? What kind of structure is going
So basically, what you do, you calculate based on the order structure, energy minimize order structure. Because this order structure is not possible to calculate. So and then you check, you do nearest neighbor atom exchange, and again try to minimize the structure. So
Basically, this is the most
minimal, like exactly. Yeah. So and then we have calculated the gamma point phonon. You can see below 50 centimeters, so many modes, and which are coming generally from heavy atoms. So these are optical phonons. So let's see what is the heat capacity. So heat capacity we have measured, and this heat capacity generally follow D by model for a solid, right? It actually accounts for the acoustic. So but we could not fit this low temperature heat capacity up to 2 Kelvin, what we have measured, by simple D by model. We have to invoke this Einstein mode, which takes care about this like low energy phonon modes. Once we have this, okay, once we have this Einstein mode included in this Debye Einstein model, there is a very nice fit, and we get very low energy optical modes, which are actually seen by this calculation. So that explains how this thermal conductivity of this compound is ultra low. Okay. So then, like we have done a high pressure X-ray diffraction as well as high temperature X-ray diffraction. As the bonding is soft due to this metavalent bonding, we should expect this R3 bar structure should go to FM3 bar M structure at lower temperature. But GAC goes like 920 Kelvin, while we see around 500 Kelvin the transition happens. High pressure, the transition happens around 4 GB. What it's predicted is it should happen in 82 GB for normal use. So this it is it can be tracked by both high temperature and high pressure. So the board is shown. So then we collaborated with Gautam Sheet. He has a nice PFA to check if there is local ferroelectric instability as posed to us, and this is the data. You can see this locally this compound shows this ferroelectric instability because this is having R3 bar, sorry R3 M space group. But this is very good because we published other paper where we have explained actually this ferroelectric instability in thermoelectric material is extremely important to have. And because ferroelectric field is nothing but a softening of optical phonon. Right? That's what we need. Because optical phonon and acoustic phonon should couple, and actually optical phonon can scatter the acoustic phonon, which actually carries the heat. So this all together, this material have this metavalent bonding as well as ferroelectric instability, which takes care of the thermoelectric transport, and GAC become very good thermoelectric, around 1.3 at this higher temperature. Okay. So this is one of the example where we have applied metavalent bonding in thermoelectrics. So in the next example, I'll come back to this slide.
Purely we can conductivity can
That should not go together. But this is that problem.
fundamentally
Fundamental problem. I know. Leakage. Yeah, leakage will happen. The thing is that so this if you measure for a pellet, you will not get sick ferroelectricity. So basically the local ferroelectricity we have.
But you think it's surface ferroelectricity?
Like with that we don't know because it's local or surface because it can be tracked only by PF. But we see basically low energy optical, which are actually ferroelectric.
and how all these parameters
Yeah.
they are actually macroscopic parameters.
Yeah.
And how do that local
Yeah.
ferroelectric will affect? It is very hard to
Visualize. So local ferroelectricity, what it will do, like so local ferroelectricity can come from many reasons. Okay, that I tell you, I have not told here. So because this compound, if you see very carefully, I didn't talk about lone pair. That I'll talk right now because it has a Bismuth 6s to lone pair. So what I believe in this compound, that locally the octahedras are distorted because of Bismuth lone pair expression, which is called inert pair effect, which is actually breaking the inert pair effect in this. So that's what we are. We have the synchrotron data, which is basically synchrotron PDF data, but we show the local structure is different from the global structure. So globally the structure is not ferroelectric, but locally it has a ferroelectric instability, which actually generates lots of low energy optical. But of course, for thermoelectric, global ferroelectricity is no, it cannot. So, let's see the lone pair effect. I'll tell you in this material. So, in topological material and thermoelectric, as I told you, it has heavy metal, chalcogenide, where it's connected by low thermal conductivity, high CMEC value, and whereas topological material has having band inversion and strong spin-orbit coupling, and metavalent bonding and thermoelectric, it has high donation parameter, so lattice anharmonicity, and high bond effective charge. It has high chemical polarization, so then they have low thermal conductivity, and moderate electrical conductivity gives rise to a new thermal equilibrium. So now, what if we combine topological property with metavalent bond? So let's see what happens. So this is a known compound, thallium BiSC2, and it is predicted and by RPS it has shown it is a 3D strong topological thallium BiSC2. And we all know the structure of bismuth selenide. It has a quintuple layer and van der Waals gap. Again, quintuple layer BiSC, BiSC. That quintuple layers are there, 5 layers. And but in thallium BiSC2, these gaps are closed. So, yeah, I have this bismuth selenide layer, then thallium selenide layer, and bismuth selenide, thallium selenide, bismuth selenide goes like that. And thallium and selenium forms a octahedra, and bismuth and selenium also forms a octahedra. Both are electron deficient. Because bismuth and thallium does not have the octet figure to form this octahedra. So these are both are electron deficient. So let's see what happened to this material. So then we have measured the thermoelectric transport property. Don't worry about the solid solution compound. So this compound shows moderate electrical conductivity, good Seebeck coefficient value, and very low thermal conductivity, and this is a negative Seebeck coefficient. So N-type materials are very rare in thermoelectric. So this is one of the best N-type material in thallium zirconate. One of the highest N-type thallium zirconate mold in the world. So then we try to understand what is happening here. So then why the compound shows very low thermal conductivity, because you see, without nanostructure it touches almost the glass level, right? So what is happening? So then we have done synchrotron X-ray pair distribution function analysis. So this experiment has been done in Petra Desi. So what we do generally, we take very high energy X-ray data and very high Q data. Q is basically scattering vector 4 pi sin theta by lambda. So we Fourier transform this Q high Q data to the like real space, and then first peak. Then we get this basically GR versus R. R is the bond length and GR is the pair distribution function. So this is a simple concept of radial distribution function in statistics. Okay. So first peak is basically the first nearest neighbor. Second peak is the second nearest neighbor, and so on. And then once we the correlation dies down, I can tell is the correlation length for a particular compound. So basically, this technique can not only tell the global structure of a compound, but also can tell the local structure. So it has a very powerful technique. But normal crystallography, like single crystal diffraction or powder diffraction, you only get a global structure. You don't get a local information. So that thing averages out and only get global structure. But this technique, you can get local as well as global structure. So that's what we try to probe. And this is the synchrotron XPDF data, and the red lines are the fitting. So this is thallium BiSC2. The structure was known for a long time, as I said, thallium octahedra, bismuth octahedra, along NOC direction. Okay, so so this single crystal data, we use the same structure file and try to fit the PDF data. You see, the first peak is not explained by the global structure. So basically, then what you have to do, you have to give some distortion to fit this peak, and get the layers are distorted like that. So layers are basically having a pseudo share with the thallium AC layer. So why it is like that, right? So this compound, although the structure is derived from bismuth selenide, the van der Waals gap compound, we are forcefully closing the van der Waals gap, but this compound does not like it. So they try to open up a little bit of the gap by shearing this layer. So that's what we got from the PDF data, and that explains both global structure and local structure.
The distance? What is the distance? Interlayer distance.
See, here it's much lower than a van der Waals gap. With thallium selenium distance is slightly higher than covalent bond distance. Whereas bismuth selenide, you have a van der Waals distance around 4 angstrom, but here is around 3.19 exactly. The second decimal. Okay. It's slightly higher than the covalent bond. So so then we try to understand why this distortion. What is the chemistry behind this distortion? Now, if you see in this compound, thallium BiSC2. So I don't have the formula. So this thallium BiSC2, the compound. So thallium, the electronic configuration is the outer shell is 6s2. Bismuth is also 6s2. Right? So and if you go down the periodic table, basically load pair should not express double. That is called inert pair effect, and this is well known in inorganic chemistry. But this kind of compound, as some of you will be knowing from the ferroelectric field, like the bismuth manganese and all this compound, the load pair expresses very local, okay, and that creates local dipole. So then exactly similar effect we see by PDA the bismuth and thallium actually lone pair expresses locally. But that should actually explain the local distortion of the structure. But why the global structure also few units is distorted? Okay. Because this local distortion of the local perturbation of this distortion created by the lone pair has been taken 2-3 unit cell away by this metavalent bond. Because metavalent bonds are basically electron deficient bonds which are highly polarized, short bonding. So if I have a local distortion, it dies up. So that's why these compounds are highly soft, which is created by this lone pair distortion, which is taken mediated by metavalent bonding. So that's why we see ultra low thermal conductivity. Now you can ask the question: how do you know these lone pairs are involved? Because if the lone pair is expressed stereochemically expressed locally, it should actually form kind of a bonding interface, right? So how to do that? Yeah, so we have done like fat band type electronic structure calculation, and the valence band you can see there is a involvement of the lone pair, 6s lone pair of thallium and bismuth, red and blue color for the for bismuth and thallium. So those are actually creating valence band, right? We are creating like NS2 NP interaction. NP is from the selenium. Okay, so this I'll show you the MO diagram what we have drawn from there, and from the basically like ELF plots or charge density plots. So the bismuth selenium is a very nice covalent bond, whereas thallium is more actually gone towards ionic but not fully ionic. Okay, so that understanding we have from this plot, and then we have collaboration with US, we have calculated the partial Conan loss, and you can see the valence band is having constructed by this YOLO. YOLO is nothing but the selenium, and this small blue and red one is basically coming from the s orbital of thallium and bismuth. So they actually mixes in the valence band. So now then we have done a calculation called 2, which tells that what is the bonding type. Is it bonding or anti-bonding? For example, if I have anti-bonding orbital in chemistry or in home, this is called valence band, right? And I think if I fill up electron in anti-bonding band, so basically the bond become much more softened, right? The bond order decreases, right? So that extent why this like metavalent bonding coming in this compound. Because why it is electron deficient for an extended compound. For example, all of you all know about oxygen molecule. The bond order is 2, right? If I go to a superoxide, O2 minus, it becomes 1.5. Peroxide, O2 minus equals 1, right? So the electron fill up in the anti-bonding, more and more oxygen molecule. Here, electron fill up in this anti-bonding orbital, which is created by the expression of the lone pair, which actually creates this local distortion. So that anti-bonding fill up gives you the extended structure electron deficient, making it metal. So this is the origin of metavalent bonding in this compound. So then we have drawn this MO diagram. So we have my student myself have seen like many days to draw this MO diagram, and that because basically this bismuth 6s and thallium 6s lone pair, which first interact with this p orbital of selenium and form this antibond. Okay, and from this antibonding actually interacts with this p orbital of thallium and bismuth. This is called secondary orbital interaction. If you know the MO diagram well, so then this level comes near just below the Fermi level with the anti-bonding character. So this anti-bonding character electron fill up actually gives this property in this compound. So and then Umesh has calculated the phonon. You see these 3 acoustic mode, but very low energy optical modes, which actually have a avoided crossing. And this feature is very important to have low thermal conductivity. This is the avoided crossing feature. So and then from the eigen modes visualization of a low energy mode, this 50 centimeter mode, you can see that this is simple shearing. Thallium and bismuth shows this kind of a shearing behavior. So that tells that what we show in the experiment validated by theoretical calculation. So what we believe now, because this we have seen the energies of the structure, the undistorted and distorted structure. So if we consider the undistorted structure and this local distortion creates manifold degenerate local minimums. And we believe, we don't have the proof right now, we believe the structure hops from one minima to another minima, and that's why the compound becomes so low thermal conductivity. And we believe if you can create more and more minima, one can have a glassy-like nature of thermal conductivity. We have seen in another compound. This compound shows crystal-like thermal conductivity. So then these are the descriptor for metavalent bonding. Electronic conductivity is moderate, 400 Siemens per centimeter. Effective coordination is much lower than 18. Optical dielectric constant is above 15. One effective charge is also anonymous, and mode specific potential current is 7, much above than the descriptor. So metavalent mediated lattice sharing we observe, and that bonding, what we believe is very unique to this class of quantum material. So this is a strong topological insulator. We have another compound right now, but it's not really unpublished. But we see this kind of heavy metal based chalcogenides, which shows good thermoelectricity and good both are candidate for topological quantum material insulator or LCM metal or some other. So they, at least some of them, what we study have this metavalent bonding, electron deficient bonding, which is one of the key to have having softness in the material. And so directly we cannot tell this is the only connection, but we believe this is one of the connection. I'm sure, and we are working in this, but we are not worked much in this area till now. So I have some time. Okay, sure. So I'll quickly finish one more. Okay. I'll just change the gear and tell you something different in solid state chemistry, which is called phase homology. Okay. So homologous series is a concept of mathematics, right? That was borrowed to solid state chemistry in 1950s, 1960s, and they created homologous compound. So as a solid state chemist, I say homologous compound. If you can identify, that is a compound generating machine. You can generate as many as compound. It's the same formula. Okay. Or like changing the formula in a particular mathematical way. So this is the NaCl type of structure, one cut of NaCl. So this is the NaCl structure. If I cut like this becomes sp2sp3 structure. If I cut like this, it becomes Cdi2 structure. If I cut like this, it becomes Bismuth Bi2sp3 structure, right? So now if I combine this Bismuth Bi2sp3 structure and Cdi2 structure on top of another, I can create new compound, right? So this is called if I have two CDI to one Bismuth selenide, then I have another new compound. So if I generate a formula out of it, this is a compound generating. So these are called homologous compounds. That has been studied over the years by different people. So and that has been studied in oxide. But we are one of the group in the world which are working in homologous compound in metal chalcogenides. For example, now all of us knows Bismuth selenide and Bismuth is very important topological quantum material, very important formula. If I write down the formula Di2m, Di2x3n, and change the m and n, for example, if n equal to 0, I have Di2x3 structure. That everybody. So now, if I say one compound is BISC, okay. So BISC is a compound which will have m equal to 1 and n equal to 2. So I have Bi6x6. So basically, this compound is BISC, and which is a weak topological insulator. This is a strong topological insulator. This is a weak topological insulator. And Bi4Ac3, which is nothing but m equal to 1, n equal to 1. This is another compound which is called topological insulator. So by changing the structure, dual topological insulator means you have basically weak topological insulator as well as topological crystalline. That BIT is that dual topological. Yeah. So mixture of weak topological insulator, because some of the surface states are protected by time reversal symmetry, and other part of the surface states are protected by mirror symmetry. That is the topological crystalline. So both phases coexist in PIT. This is very interesting. So by simple identifying the homologous series, actually we have generalized these compounds can be generated from the same series. So this is called a homologous series. So now you can think like X can be selenium, tellurium, Bismuth can be replaced by antimony, or like other group 5 element, and I can generate very compound. So this is basically machine learning in synthesis. Okay. So then this is the compound BISC. As I told you, it has a Bismuth bilayer and Bismuth selenide in between, sandwich between like two Bismuth selenide. And this is a simple Bismuth selenide compound. So let's see what is the thermal property of this. When we measure the thermal transport, this BIC is ultra low, which is a weak TI, and the strong TI shows high. Right? So then we dig down deeper and understand from the phonon dispersion. So this is BISC. The pink colors are coming from the Bismuth bilayer Bismuth. So this Bismuth bilayer Bismuth. So low energy optical phonons are coming mostly from Bismuth bilayer. But whereas here low energy optical phonon modes are coming from the normal Bismuth, covalently bonded Bismuth. So then what we have done, we have visualized this mode and find it out. We have the lattice share. So basically, in the structure, this bismuth bilayer shared within this layer gives rise to this low energy optical. And those optical modes again we have seen by capacity experiment, low temperature experiment, which shows boson-like hump as well, which is observed in visual class. So this is very interesting compound, which the property actually governed by this layer, which is actually heterostructure compound, and this layer gives rise to this weak topological insulator behavior. So the bonding in a solid and structure is actually connected between topological insulator as well as thermoelectric. So that's why I wanted to say like chemical bonding plays a very important role. So that I'll finish it. So the set is quite good. We can enter 0.8 in this material. So then we have actually patented it because this is near room temperature. So this can compete with N-type bismuth. So and selenium is much cheaper than selenium. We have patented it, and with our patent, actually Tata Steel started working with us, B-type and N-type material. So with collaboration with Tata Steel as well as ARCI, we made scale up in our lab up to say 200 grams of this B-type and N-type compound, and these are chopped into small pieces. And we have created multiple legs. And recently in Tata Steel plant, they have like inaugurated a thermoelectric generator of 1 kilowatt, and where some of our B-type and N-type material and devices have been. So they are actually the Tata Steel. The target is basically the blast furnaces are cooled by the steam. The steam temperatures are around 120 degrees. So and this material so speak exactly that. So basically the Tata Steel what they say like waste heat coming from the steam pipe can be converted to electricity, and some of their lighting can be done. So we are funded for last 3 years by Tata Steel. With this, I come to the conclusion. So beta-valent bonding is a one-pot recipe to thermoelectrics that can manifest like novel emergent property in the material. Because and this bonding is unique to this topological quantum material and thermoelectrics. This is most important. And I have shown how one covalent compound can be changed to metavalent compound, and it can become thermoelectric. Another case I showed is beta-valent bonding in a 3D topological insulator, how the local lone pair distortion can be transmitted to a slightly longer scale by polarizable bond and give rise to high thermoelectric performance. At the confluence of topological quantum material and metavalent bonding in chemical sphere is a rich field of exploring thermoelectric research and activity. And one news came in DST website about our recent paper, which is about the chemical bonding in topological quantum. With this, I acknowledge my excellent collaborators. And this two gentlemen actually helped me to give this talk. Basically, we have collaboration for both of for different purpose of low temperature measurement as well as theoretic measurement, and mesh for theoretical calculation, and generous fund from ACRB, DST, Tata Steel, JNCASR. Thank you all, and of course, they actually generated new ideas. I just keep talk here. So thank you all, and I'll be happy to answer. Thank you.
So, thank you, Kanishka, for the wonderful talk. So we can have some questions. Yeah, one.
So, the last compound, what's the purity level? Because bismuth selenide is lots of
Antisite.
Antisite depends nothing to do with purity.
Yeah.
So defect is an intrinsic property. Purity means you have something else, some other.
Foreign.
This is 100% pure compound. Okay. So you can tell selenium vacancy is there or not. Okay. But purity is a different chemical word, and vacancy is a different chemical. Vacancy. Like of course, is selenium vacancy because the Fermi level is in the basically your conduction. Okay. But if it is like purely basically vacancy free sample, the Fermi level should be in the middle. Conduction band.
But then if you have this impurity, then
It's not impurity. It's vacancy. Yeah.
Okay.
Yeah.
So these things are going to create an anti-site look like it.
Yeah.
In your sample, there's no.
Of course, it is there because it is intrinsic to this. Because if you have a selenide, it is an intrinsic. You cannot avoid. Sulfide is more because the vapor it comes from the synthesis. So if you go from tellurium to sulfur, selenium to sulfur, the vapor pressure is lower, right? So this is anyone try to synthesize this compound, it will always have that. This is intrinsic to the charcoal. But if you go down the periodic table, the vapor pressure become higher, and then it becomes more vacuum. Okay. So now how we can do? But vacancy is a good person. I don't know.
I'm worried about more about topological.
Yeah, topological properties. So that is the problem of experiment. That is, they cannot measure if they have a vacancy. But vacancy is intrinsic.
In this scenario,
Yeah.
you have conductivity not only from
Surface state,
but also
the bulk state.
so how it is going to affect?
So basically, see, so what you are asking me question like, are you measuring conductivity from bulk or surface, right? Yeah. So what we are measuring from bulk measurement from both. We don't differentiate because that is already understood. This material is a topology. We are not claiming this is not a topology considered or topology. What we are trying to understand here how this topological like quantum material property is related to chemical bonding and how it improves the thermal.
But in your case, you need low thermal conductivity or high thermal.
Low thermal.
So then, what is the ideal situation? Like having Fermi level intermediate?
See, see, low thermal conductivity, that is thermal conductivity. Nothing doesn't matter like what the electronic level is. Now you talk about the electronic part of thermal conductivity. It can be doped because I need a high electrical conductivity also, right?
Yes. That helps.
So that's what for thermoelectricity. It does not matter where the Fermi level like here. It matters only when it shifts from valence band to conduction. Then the battery will become p-type. But if it is slightly low, that's okay. Not a problem.
Actually, electrical part if you disturb, you immediately conductivity will disturb K by sigma.
Right.
So I think we always have to deal with phonon.
Yeah, because that is only independent.
Yes,
Right?
okay, it is independent.
Because Shibek is also related to Shibek.
Yes, Seebeck is related, but somehow Seebeck is not related to carrier density. But
I'll tell you how it is related.
that's
So,
right. No, but for example, that semi-metal low carrier density but high mobility that helps conductivity
Right.
as well as
but
thermality.
Shibek, if you have so much carrier, the Shibek actually dies down. Because if you see the multiplication, Shibek,
Yeah.
the car
High carrier. Yeah.
but if you have a multi-valley system, so you need slightly. So for example, if your band structure is like this, yeah, I have a value, few millielectron. Okay. So if my Fermi level is here, I have certain Shibek rules. And if this band, say for example, sharp band, this band is a flat band, so high M star is directly related to the Shibek rules. If I put the Fermi level here, I have this contribution and that contribution. That is the M star, high M star. So that time my Shibek rules is that the play around how you put the Fermi level. So, any more questions?
So this local distortion, you were telling, is it not affecting the global space, the space group?
No. Globally, if you try to solve, you will get the global structure. The local structure, actually, the local distortion died out of the sun. Few units.
But those distortions were real. So,
The distortions are real,
but then then the bond
but in
dynamics will
longer
be
scale, that averages out. But it affects the property. Basically.
Also, I think it's density. How many? If it is too much in number, then we will.
It's too much in number, but the exactly opposite way that it happens, and in global structure, actually, it averages out when you solve the structure. For example, so when I give a talk on fully on PDF, I show a picture. Like for example, for this room, if everybody sits in line from a distance, you will see everybody sits in line. But if I come and check, there will be slight shift on the line. Okay, so that is the way to check by PDF, basically.
In that structure, like at the TL, is that phonon mode associated with the TL layer and the charge transport to another layer? Can that
Very good
happen?
question. Very good question. Because see, thallium and bismuth both are heavy. So we believe both contributes as phonon loss shows
Both are contributing.
to the phonon. Both are there. Thallium is more because it's much heavier. Low energy thallium is more, but bismuth also has a contribution. So, but of course, thallium has because if you see the phonon also, thallium bismuth both contribute to this. So, but charge transfer fully happening to this layer, that claim, of course, we thought, but we don't have a proof right now. So that's why I don't say. But some of the compound we made it, that actually it creates channel for phonon and
Different routes.
different groups. So I don't see any more question.
So I thank Kanishka for this wonderful talk. Thank you very much.